Well, don't forget that this evening you have your final project, the third project to finish up. And so whatever you've submitted to the scoreboard by 5:30, I guess it is what your score will be on that. It'll stop accepting submissions after that. So don't forget to get that all updated and get your stuff submitted. And then Tuesday, plan on having our second test. Wednesday, the final homework. Yeah, you just put the -S thing in and that'll send it over to the scoreboard and it'll check it out, make sure it works, and put the grade up on the web page, or the score rather, not the grade. Okay. So everything up to the point that we take the test is always what's covered on the test. And yeah, we'll have some stuff to refine. After Tuesday, we'll have 3 more classes to nail down some concepts, make sure we tie a bow around the course, get everything uh, finalized in some form. So, with the 9 weeks that we have to work on it under the circumstances, we've made relatively decent progress, I think. So, we want to talk today about more about virtual memory and translating virtual addresses to physical addresses, which is really important thing to understand how that actually gets accomplished on the computer. And so just to look at the sort of the general concepts before we go into the specifics, we have, as we noted yesterday, we can look at the translation of the virtual address to the physical address as sort of a mathematical function that maps things from a address space of virtual addresses to physical addresses. And it shows union, the set containing the null set. And that's because that not all virtual addresses are mapped to a specific physical address at any given point in time. And that's this case down here. And there's actually two subcases. If it's not mapped to a physical address, it could just be that it's in the backing store in the page file out on the disk and needs to be brought into memory, right? A page fault. But it could also be that that slice of your virtual address space has never been made active. And so if you've tried to reference some memory that's not even mapped as part of your active virtual address space, then that's what we call a segmentation fault. And that's when you get those errors, typically from some really bad array subscript or mangling a pointer, then dereferencing it, pointing off into some arbitrary address that doesn't really map to any of your active virtual memory range. So there's two subcases there when it wouldn't be mapped to an actual physical address. We're going to have a whole bunch of terminology we have to use. So we have to come up with some conventions for the nomenclature. And so when we refer to our virtual address space, this big, huge virtual address space that each process thinks it has its own virtual address space, we'll refer to the size of that as capital N, and therefore there'll be little n bits required to address something within the virtual address space. We'll refer to the physical memory on the machine, however much of that you have, 4 gig, 8 gig, 12 gig, 16, whatever it is. We'll refer to that as M, the total amount of physical address space you have on the computer. And then, of course, that would mean that little m is the number of bits you would need to reference a byte within that range of possible addresses. And then P will be our page size. We're going to slice both the virtual and physical memory into the same size chunks called pages. On the actual real computer, these pages will be 4K in size. And so you can think of that as being when we're flipping things in and out to the page file, to bring a piece of your virtual address space into the memory of the computer and make it active. That's the size that'll be happening in, is those 4K pages. This stuff doesn't make any sense at all, TLB, and we'll talk about that in a minute, and that'll make more sense. And then this stuff down here at the bottom is just talking about the physical caches that we've been talking about last week, the offset of the byte into the block in the cache and the index into the cache and the cache tag. So that's all the same stuff as what we've had before, but we'll talk about this more when we look at a specific example and after we explain what this TLB thing is. So let's just see what would go on if we generated a virtual address and we wanted to translate it to a physical address. Well, we're going to have a page size. And so in our case, say 12 bits over here for 4K pages would be needed to reference a byte within a page, right? So you can think of that as an offset within a page. And then this number of bits over here would just identify the different pages, right? Page 0, page 1, page 2. So if you start incrementing these bits here, you're just enumerating all the pages of virtual memory, and this is selecting a byte within a page, right? And so to translate the virtual address to the physical address, what we have to do is we have to make an association between a virtual page number and a physical page number so that we can generate an actual physical reference to memory, right? This is the thing that we've been looking at about how it bubbles down through the cache, this physical address, right? So to do that, we need a thing called a page table. And the page table would simply be this big array, and it'd have a valid bit, just like we had before, saying the entry in the table is valid. And what would be in there would be for a given virtual page, you go subscript down here, and then you'd get the corresponding physical page, and then you could put the physical address together and go reference it. So we need this translation of the virtual page to the physical page, right? So that's the basic concept. So how do we do that? Well, we'd have a thing called a memory management unit, and the CPU, as it's executing your program, generates a virtual address. And this page table, this thing shown here, where does it live? Well, it would have to live in memory, right? It's got to live somewhere. Well, it's in memory. So this is showing that, well, this page table is actually in memory somewhere. So when we generate the virtual address and we give it to the memory management unit, it wants to access that page table, look up the page table entry, right? In the page table. Well, that's actually accessing physical memory to do that, right? And like all things in physical memory, it would be subject to being cached up in the hierarchy of L1, L2, L3 caches, or not. Maybe it's just laying in RAM somewhere. But in any event, this is trying to illustrate that that reference to the page table is actually a actual physical memory reference. And then we'd get the page table entry, the physical page number out of the table. And now we could form the full physical address we wanted in the first place and go to memory again to get the contents of it. Well, this doesn't sound real good, right? Because we've noted that the slowest thing going is touching memory, right? And so now you say, oh, I got this concept called virtual addresses. But in order to implement these virtual addresses, now I'm going to touch memory twice for every time I want to get something out of memory. I got to go to the page table to get the physical page number associated with the reference. And then I go back to memory to the actual thing that was trying to access, right? Where is it? And so is my computer going to run half as fast as it did before I implemented this crazy virtual address stuff? Well, not really, and we'll see why later on. The next thing that could happen, which would be even worse, is when we go to get the entry, it's not in the page table, right? That valid bit wasn't on. And so that's going to cause a page fault. We got to vector up into the operating system. The operating system is going to run some code that's going to say, oh, I got to deal with this page fault this process generated. I got to initiate a disk IO to go get this thing off the disk maybe and bring it into memory. And then I got to manipulate the contents of his page tables. A lot of stuff going on there. And then I got to put the process back into execution to redo the instruction that it did that caused the page fault so that this time it'll actually work because the thing it's after has been brought into memory. So that is going to be hugely expensive amount of time, which is going to make things run really, really slow. So this is not shaping up to be all that great. Why are we going to use this virtual address stuff if we're just going to slow the computer down to a crawl in order to do it? Well, we have ways around it. So this is showing that the virtual memory references that are these translations of the virtual page numbers to physical page numbers, like all references to physical memory, are subject to caching. So if we get lucky, a lot of these page table entries will be bubbling up into the cache. And so when we reference those memory locations where those entries live in the page tables, we'll be hitting in the L1 cache, we hope. And so that will, to some degree, ameliorate the problem of why did we make the computer run a lot slower to do this virtual address stuff? But that's not the total solution to the problem. The real solution to the problem of this scheme is going to really slow things down is to build yet another form of cache, a thing called a translation look-aside buffer. And the whole purpose of this cache is to simply cache up entries out of page tables, the associations between virtual page numbers and physical page numbers. So the way this device is built is every time you actually get something out of a page table, out of memory, it caches that up into this TLB cache, translation look-aside buffer cache. Now, if I go back to get that same virtual page, I've got the physical page associated with it right in this little TLB cache, and I don't need to go to memory to the page table to get that. I can go ahead and just form the physical address without touching memory twice, in other words, right? So that's the whole purpose of this TLB is as you pull things in and you touch them out of the page table, they get cached up in this special cache called the translation look-aside buffer so that we can hopefully, reuse them a bunch of times because you'd probably be accessing things within that same virtual page if you had any locality at all, right? And we can cache up a number of entries. So a collection of things out of your page table could be sitting in this TLB. And then we wouldn't have to be going to memory to get the translation of the virtual page to the physical page. We'd just be getting it out of the translation look-aside buffer. So that's the real solution to why isn't this virtual memory stuff going to make the computer run half as fast? It's because we build this little special piece of hardware called the TLB to get out of that issue, right? So what that looks like is the CPU generates a virtual address, and now we want to get the virtual page and push it into the TLB like a cache, right? And say, do you have in there the corresponding physical page number associated with this virtual page number? And if we get a hit in the TLB, yeah, that's in there. Then we get the physical page number and we can form the full physical address, right? And then we can just make the memory reference. So there's that one memory reference back rather than going to the page table, getting the thing. So sometimes you got to go to the page table, but hopefully your code is exhibiting locality to a sufficient degree where it's going to cache up the virtual page numbers that you've been referencing. And once it warms up this translation look-aside buffer, you're not doing double accesses to memory for every virtual address that you're trying to access, right? So that's the key to why doesn't this make it run half as fast. But it's possible that you get a miss in the TLB. It's a cache after all, it doesn't have all the entries from the page table. And so when that happens, you actually have to go into memory and access the page table. But when you do, the way the thing is wired up, that entry out of the page table gets cached up in the TLB. So that if I reference that virtual page again, it's already in there, right? So I could hit in the TLB or I could miss in the TLB. If you miss in the TLB, you got to get the translation to the physical page out of the page table, which lies in memory, right? So that is kind of talking about, well, what are we doing to get around this virtual address thing seems to want to make things run real slow. Got to hit memory twice for every reference, but not really because of the TLB effect, right? The other issue is what about the size of these things? Well, let's suppose we had 4K pages, which is what we really have on the real computer. So that takes 12 bits. So the rightmost 12 bits of a virtual address you can think is simply defining the offset within a page, right? Which byte within the 4K page do you reference? And all the bits left over to the left as defining a virtual page number, right? Which virtual page are you talking about? Well, then what would we have if we had a 48-bit virtual address space, right? Well, if you have 48-bit virtual address space, how many bits are going to be used to describe a page number? Well, if you had a page size of 12 bits, you'd subtract the 12 from the 48 and you get 2 to the 36 different page numbers you could generate, right? So this is trying to show that here, 2 to the 48 times 2 to the minus 12 is showing, okay, I've got 2 to the 36 different page numbers I can generate in this 48-bit address. And for every one of those page numbers, I got to have an entry in this page table that shows what the physical page is associated with that virtual page number, right? But how big is that? Well, suppose I had 8 bytes per page table entry, which is really small, but suppose it was like a 32-bit physical address, you're saying, right? So if you just ignore any kind of bookkeeping valid bits and all that kind of crud and say, okay, well, you probably have at least, 8 bytes in there to represent a 32-bit physical address that goes over to there, points at the memory somewhere. So I need a page table that has how much space? 512 gigabytes. Where does that live? Well, that would have to live in memory. Oh, wait a minute. I don't have 512 gigabytes on the whole computer. And you're telling me to just hold the page table for one process, I need 512 gigabytes of memory. Well, that obviously isn't going to work, right? And I've got hundreds of processes. And I want things other than just their page table. I actually want the contents of memory that they're occupying, right? Not just how to translate virtual addresses to physical page numbers. So this obviously isn't going to make any sense and work on the computer to do it that way. We're not going to have these 512 gigabyte page tables for every process, right? So the answer to this problem is to use hierarchical page tables, which we'll explore in more detail later. And we'll find that on the actual real computer that we're playing with, we have a 4-level deep hierarchy of page table entries. So the key is that if they're showing a 2-level one here, for each one of these entries that you'd put in the level 1 table, he points to something that's a table that could have a whole bunch of entries in it, right? So suppose this was a page of memory, this level 2 thing, right? That would be 4K of memory. And suppose each entry took 8 bytes once again, right? So I could have 512 entries in here that pointed to physical pages of memory. So for one entry here at the top, I get 512 pages of actual physical memory that get mapped through there, right? So that's the key to why this hierarchical scheme is going to save us a lot of space. But to make it make sense to you and see how it works out, don't worry so much about it now. Wait till we see the actual real one, and then you'll see how it's working out, right? So 2-level page table, they're trying to draw you a picture with 32-bit addresses. You have the actual virtual memory that you need to cover all these entries for your virtual memory. And they're showing that one single entry at the top could point to a table of page table entries. And you could have like maybe 512 of these ones that you could service out of this one entry there at the top. So that's really going to be the key to why that's going to work effectively for us and end up with a lot less space than having to have an entry for every single possible um, page table at one level, right? See, a lot of your virtual address spaces at any given point in time, not even in use, right? So if I had this one big Gonzamundus level 1 table that had to hold everything, that'd be my 512 gigabytes I'd need for that. But really, I'm only using certain slices out of my virtual address space. So a couple of entries here that in turn point to things that have 512 total entries possible, maybe, right? That could service a lot of stuff that I have active in my virtual address space without requiring a big, huge collection of stuff in these tables, right? So that's really what's going to happen there. So just the concepts that we've been going over about virtual memory, right? Now we want to get down lower level and look at the specifics of how these things actually work on the computer. But to get there, before we get to the actual real computer and look at it with its really big, wide number of bits and all this kind of stuff, like always, we want to look at a little small example that'll fit on the slide with a fewer number of bits and just see how it would work for a computer with a smaller address range, right? So that's what we're going to do. We're going to look at a simple memory system example, and then eventually we'll look at the actual Core i7 running on a Linux operating system and how the virtual memory is managed by the operating system and what all the tables look like and what size they are and how they get used by the hardware. So to review the nomenclature, we're going to have all these different things that we'll be using to become clear in just a second. What now that we know what a TLB is and the fact that it's an actual form of a cache, well, then it's going to have cache tags and cache indices just like any cache. So we'll see how all that works out in just a second. So to simplify it, rather than dealing with the big 64-bit or 32-bit thing, let's suppose we had a computer that had a virtual address size of 14 bits, because it'll fit on the picture here, right? And the physical address size of this make-believe computer is going to be 12-bit physical address. So how much physical memory can this make-believe computer access? What's the total amount of memory you could possibly have, physical memory, on this computer in our example here? Anybody? Somebody tell me how much memory this computer can support with 12-bit physical address. Well, if it was a 10-bit address, how much memory could you support? With 10 bits, you can discriminate between how many different things? 2 to the 10, right, which is 1K. So if I have 12 bits, how much memory can I address? 4K, right? So this silly little example computer here could support a total amount of physical memory of 4K. Oh boy, right? How about my virtual address space of a 14-bit virtual address space? What amount of virtual address space does each process think that it has to play in? Well, 14 bits is 16K, right? So I have a 16K virtual address space for each process that's being mapped down to a total of 4K at any given point in time, resident in memory, physical addresses, right? So I want to have 64 byte pages. The real one has, you know, 4K pages, 12 bits. For 64 bytes, I need 6 bits, right? 2 to the 6. So the rightmost 6 bits is just a number that's identifying which byte within the page are you referring to. It's the offset, the virtual page offset. And the bits on the left, the ones that are left over, are identifying which page are you talking about. So this says which page, and then within that page, which byte are you talking about, right? 64 byte pages. If I put zeros on the left, I'd be page 0, and then you'd have all the possible combinations here of the bytes that you could address in page 0. And then you go to 1 here, and then you'd have all the combinations of things you could address as offsets within page 1, right? So that's how you slice up the bits in your virtual address. It depends upon what the size of the pages are you're going to play with, right? In this case, there's 64 bytes, so we need 6 bits as the virtual page offset. All the remaining bits then just enumerate which pages in the virtual address space we're referring to. Similarly, the size of the page for the physical pages of memory is going to be the same size as our virtual page. And so that's going to be 6 bits that are needed to select a byte within the physical page of memory. And it's the same number that we had here. We just drag it down and use those same bits as the offset into the physical page, right? But the translation happens in taking the virtual page number and translating it into a corresponding physical page number. So that's where the magic happens, right? That's where I have this bigger virtual address space that's mapping down to some subset in memory at any given point in time of physical pages in memory, right? Everybody okay with that idea? So presumably, since I have um, 8 bits of virtual page number, how many entries would I need if I just had a one level, no hierarchical thing at this point, a one level page table with entry in it for every virtual page? Well, I've got 8 bits, so I need 256 entries in my page table, and each of those entries is going to be the physical page number associated with that virtual page. So this is showing the page table, but instead of showing you the 256 entries, they're just showing you the first 16 of them, right? just to fit it on the slide. So the page table would have, you go to this subscript down into the table with this virtual page number, right? And you pick up the physical page number that's stored there. And of course, there's a valid bit saying whether or not it's valid. In this case, meaning valid is meaning that it's memory resident, right? It's actually sitting in memory somewhere as opposed to a page fault where you got to go get it off the disk and drag it in, right? So this would be kind of what the page table would look like. And then here's what our translation look-aside buffer of this make-believe computer is going to look like. The translation look-aside buffer in this case is a cache, right? And it's going to be a four-way set associative cache in this example. And it's going to have a total of 16 entries. Well, if you have 16 entries and your four-way set associative, you have 4 entries per set, then you have a total of 4 sets, right? If I have a total of 4 sets, I need 2 bits to select the set. So there they are. The bits on the right are selecting within the page, right? This is the virtual page number on the left. I'm going to make that virtual page number and push it into my TLB to see if I got a hit on translating this virtual page number to a physical page number. So I'm going to use these 2 bits as the index into the set associative translation look-aside buffer, subscript into one of these 4 sets, and then try to match the bits that are left over as the tag for the cache, right? So however many sets you have determines how many bits you need to index into it, right? And all the bits that are left over are the tag that are sitting in a TLB is just another form of cache. Only what I'm picking up out of the TLB is a physical page number associated with this virtual page number. It's caching up those translation entries, right? Does that make sense? So they're saying, suppose this is what my TLB looks like in this example for this computer. And then we got a physical cache as well, right? In addition to the translation look-aside buffer that translates virtual page numbers to physical page number. Once I get a physical page number, I have a physical cache, right? And they're saying, okay, suppose in this example on this computer, it's a direct mapped physical cache with 16 entries, 4-byte blocks. So the 4-byte blocks, I need to pick a byte within the block. Since I have 16 lines, I need 4 bits to pick an index within the thing, right? And all the bits that are left over are the tag bits that sit in the entries in the cache, right? You've seen these before last week. We talked about the physical memory caches, right? So now that we have the computer described, it is 14-bit virtual address, 12-bit physical address, 64-byte page size. Here's the page table. Here's the TLB, what it looks like. Here's the physical cache, what it looks like. Let's look at an address. We generate address on the computer, right? O3D4. So just lay that out in these bits that compose the address, right? The rightmost 6 bits, since we have 64 byte pages, is simply the page offset. And the rest of them identify which virtual page you're talking about. So the virtual page number is bits 6 through 13. All of these guys is the virtual page number. But to push the virtual page number into the translation look-aside buffer, since I have a 4-way set associative total of 16 entries, 4 sets, these 2 bits is my index into the TLB, right? So the index into the TLB is 3, and the remaining bits over here is the tag, which is 3 as well, right? Is everybody okay with that? The TLB index is 3. The tag is 3. So I want to go up to my TLB and look at index 3 in it and see if I have a tag in there of 3. Yeah, I do, and it has the valid bit flipped on. So I got a hit in my translation look-aside buffer that's telling me the physical page number associated with that virtual page number you're looking for is 0D. So that's where this comes from. The physical page number is 0D. It came out of the TLB, right? Told me that that virtual page number, yeah, is cached up in the translation look-aside buffer, and the physical page number associated with this virtual page number is 0D. So now I have my physical address I can form by putting this 0D as the physical page number, right? And then the offset bits, the pages are the same size, they just come down here, right? How does, now that I have a physical address from my virtual address, I can push that onto the physical cache to see if I'm going to hit in the cache, or I got to go to memory to get this stuff, right? So how does that divide up? Well, the computer has a cache that's direct mapped, has 16 entries, right? And it has 4-byte blocks. So we need 2 bytes for the cache offset for the block, right? Byte within the block. I got 16 entries, so I need 4 bits to index into that direct map cache. So my cache index is 5, and my cache offset is 0, and my cache tag, everything that's left over here, is 0D. So now I need to go look in the physical cache at index 5 to see if I've got 0D sitting in there. Oops, there it is. Index 5, 0D, and it's valid. What was my byte offset? It was 0. So there's the actual byte of memory I'm trying to refer to. And it was a hit in the physical cache. So things worked out really good in this example, right? Because I hit in the translation look-aside buffer in translating the virtual address to the physical address. That was good. And then once I got the physical address, I hit in the physical memory cache and grabbed that byte 36 out of the cache. It didn't have to go to RAM to get it. That's as good as it gets, right? You hit in the TLB in translating the virtual address, you hit in the cache on the physical address. Questions about that? So things can only go downhill from there, right? I could miss in the TLB and have to go to the page table. Once I got the thing out of the page table, maybe I hit in the physical cache, maybe I don't hit in the physical cache. Maybe when I go to the page table, I get a page fault. It's not even mapped to memory. So all those combinations of things could happen in trying to translate this virtual address. So let's look at another one. We'll look at 0B8F as my virtual address. So the rightmost 6 bits is the virtual page offset, 64 byte pages in this example, right? The translation look-aside buffer has 4 sets, so these 2 bits are the index. So the index is 2. The rest of the bits in the virtual page number are the tag for the TLB cache. So that's a B, right? 11. So then we're going to go to the translation look-aside buffer and look at index 2 and see if there's a tag of B in there. Index 2 is B. No. So I missed in the translation look-aside buffer, right? TLB hit? No. So now what do we have to do? Well, we have to go to the page table, right? What's the entry in the page table I'm after? Well, the virtual page number for this thing is 2E, all these bits here. So I need to go look up in the page table at entry 2E and see if I have a valid mapping for entry 2E in my page table. There's my page table, and they're only showing us the first 16, so presumably 2E is not currently mapped to anything. So that's a page fault, right? So I had a page fault when I tried to get this virtual page out of the page table. It wasn't in there. So I have a page fault. Does that make sense? So now we vector up into the operating system. He has to deal with the fact that we generated a page fault, shuffle some stuff around in and out of off the disk, maybe monkey with my page tables to make them point to different things in different physical memory pages, all that stuff, right? So that's the combination where we missed in the TLB and we didn't hit in the page table either, right? So the next one, we look at this address 0020, which means that your offset bits over here on the right are those guys. And then you have 0 in your index and 0 in your tag. So we got to go up to the table and look and see in the translation look-aside buffer at entry for the 0, whether we have a tag of 0. So entry 0 have 0 in the TLB. Yeah, but it's not valid. So I missed in the translation look-aside buffer, right? So that means I got to go to the page table, right? So when I go to the page table, what am I looking for? I'm looking for this virtual page number, which is 0, right? So we're going to go to the page table for entry 0. And what was the, yeah, entry 0 in the page table. Where's my page table? There it is. And it says, yeah, you got a valid entry in this page table for slot 0. And the physical page number associated with that virtual page number is physical page 28. So now we go to physical page 28, which means you put 28 in the physical page number and drop these offset bits down, right? And there's your physical address. So now we need to push that physical address onto the physical cache for caching up physical memory references, right? And so the offset, there are 2 byte blocks in the physical cache. So you got 2 bits of offset. So the offset in the cache is 0. The cache index, it's 16 entries, remember, direct mapped. So these 4 bits is the cache tag. I mean, the cache index of 8. And then everything left over is the cache tag of 28. So let's go look at our physical cache at index 8 and see if we have a matching cache tag of 28. Index 8, do I have a 28 in there? No, it's 24. So I didn't hit in the cache. So that means I have to go to get this address out of the memory and pick up whatever value it happens to be laying there. Questions about this? So there's two steps involved, right? You generate a virtual address. The virtual address gets translated to a physical page address. How does that happen? Well, maybe by pulling it out of the translation look-aside buffer. Maybe not, in which case you'd have to get it out of the page table. If you go to the page table to get it, maybe you get it out of the page table. Maybe the entry in the page table says it's valid part of your address range, but it's not currently in memory. It's laying off on disk. That's a page fault. Or if it's not a valid thing that's even mapped into your virtual address space, then that would be a segmentation fault. Okay. Once you get the physical page number associated with the virtual page number, now you have the physical address. So that gets pushed down onto the physical cache hierarchy, right? Everybody okay with how this real computer is going to work? Okay. So now we want to look at the real beast. You've seen the stuff on the left before. This is saying, okay, we got 4 cores, here's one of them, right? What's it look like? Well, we've got our registers, we've got L1D and L1I cache. Those are those physical caches, right? L1, L2, here's the L3 unified, shared by all the cores, right? Big 8 meg guy, 16-way set associative. That's our physical cache hierarchy from last week, right? Now here's our memory management unit that we're introducing now, right? And it's a cache, right? It's going to cache up associations of virtual page numbers with their corresponding physical page numbers. But yeah, as you might have guessed, on the real computer, that cache is also a hierarchy of caches. It has an L1 and an L2 level. And the L1 level is bifurcated, just like the L1 level in the physical cache is bifurcated. So we're caching up data references here and instruction references over in the L1I cache, right? They're slightly different size. They're both 4-way set associative, and there's a total of 64 entries in the data references, which means you have how many sets? 16 sets, right? And in the instruction references to get opcodes in the instruction pipeline, right? Your 4-way set associative with 128 entries, right? So you have 32 sets, twice as many sets in the iCache. When you get down to level 2, it's still 4-way set associative, but you have a lot more entries, right? And it's unified. It's not broken up into data references and instruction references anymore, right? So this is your translation look-aside buffer. It's a cache, and the entries in that cache are what are the physical page numbers associated with a given virtual page number reference. So I can get those without having to go to memory, hopefully. They'll be cached up here as my process is running. So since you could have total of 64 entries in here and 128 in there, 512 in there, that ought to do you pretty good, right? Because how many different virtual page numbers are you going to reference in some given burst of time by your process? You're not going to be bouncing all over your virtual address space. You're going to have some locality going, right? So when you touch those virtual page numbers, they'll be cached up with their corresponding physical page numbers. Every time you had to touch it in the page table, it gets cached up in here, right? So as your process is running for some little burst of time on the CPU, it's doing what we call warming up the TLB with things that it's referencing, right? So now you reconsider that problem that we posed at the beginning of, oh my God, it looks like you made the computer run half as fast because you got to go to that dang page table. And then you got to take the physical reference and actually go to memory to get what you wanted in the first place. So that doesn't look quite as bad anymore because we got this TLB thing going for us, right? It's caching up all these translations of virtual to physical page references as the process is running. But the virtual address space is a per process entity, right? So when I context switch the computer, none of these entries in the translation look-aside buffer are worth anything anymore, right? Because the virtual pages for the other process are completely distinct from the virtual page references of the previous process, right? They have nothing to do with each other. So I flush the translation look-aside buffer when I context switch this core onto another thread, right? So you get this kind of effect of after you do that context switch, trying to warm up the TLB. But even that is not quite as bad as it sounds, because remember when we sliced the address space in half and mapped the top half to the operating system? Those are the same for every process on the system. So those kind of tend to get bubbled up into the TLB and they just stay there, right? Because those don't get flushed when I context switch, because those are the same for every process. So we'll see how all that works in detail on the specific processor. Monday, we'll go in and translate some actual real virtual addresses on the Core i7 and see how everything actually works, right? So, questions about anything? Office hours are at 2 today. And don't forget to get your project stuff submitted. We have a test on Tuesday. Final homework due Wednesday. And Wednesday, Thursday, and Friday, we'll finish up the material in chapter 9 and kind of look back at the course and see all the concepts that we've covered and see if you have some conception gelling in your head as to how the computer actually works and what it's doing. Okay? Any questions before we go? Well, if not, maybe I'll see you later at office hours. If not, have a great weekend, and I'll see you Monday. Bye bye.